Welcome to Physics 30, the best course in high school, tied with Physics 20, perhaps, and maybe Calculus. Oh, and also Math 30-1. And these are all exquisite courses that will engage you and develop your thinking and your mind and your spirit. Okay, that's enough. So let me just talk very quickly about Physics 30. Physics 30 has 4 units. The first unit, momentum and impulse, is very Physics 20-ish. There's some formulas, and you plug in numbers, and you get answers. Then we go to electrostatics, and that becomes much more conceptual. And magnetism, third unit, much more conceptual. Actually, the third, electrostatics, magnetism, are kind of one unit, forces and fields, but sometimes we deal with them as separate units. And then we go to EMR, electromagnetic radiation, which is just unbelievable. And we finish with atomic physics, which is also unbelievable and will blow your mind, especially when we talk about quantum physics. But we start off nice and easily with momentum and impulse. It's essentially Newtonian physics based on the work of Isaac Newton. And as you can see, we have some intro videos to watch, which we're not going to do on these SmartWorld presentations, but I may send you links to these videos so you can watch them. And here's our notes, provided wonderfully by Mr. Bill Klintberg. My sincerest thanks to him for outstanding notes. And we're not going to go over all of these. You can read all this stuff about what momentum is. Let's go right to the heart of the matter here. What is momentum? Momentum is an idea that combines mass and velocity into one package. It is an idea that is similar to inertia and kinetic energy. So some people say that momentum is the quantity of motion. Inertia is the property of an object to stay at rest. Kinetic energy is the amount of energy an object has due to its motion, and it says momentum is not truly either of these, but is a mix of the two. All right, and then you can read this interesting description, and here is our first formula for Physics 30. It's an easy one. It's a super easy one. It is momentum, which we will use the letter P for momentum, and the momentum equals the mass times the velocity of an object. So if an object has no mass, something like light, then it can have no momentum, which of course we are going to disprove, and we can actually prove that light has momentum. But for now, we're going to say if you have no mass, you have no momentum. Ooh. If you have no velocity, you have no momentum. And at this point, I would show you a whole bunch of football videos, because if you don't know me already, you know I love football. American football, that is, not English football, which you commonly call soccer. Very unusual. Back to momentum. And it says, notice that momentum does not have a nice derived unit, which is a shame. Although, oh, hold on, the phone ringeth. We need to pause. How do I pause this? Oh man, recorder, where's my... Okay, we're back. We are back, and back to momentum. Mass times velocity. The units for mass are kilograms. The units for velocity are meters per second. Sometimes people put a dot in between. The dot simply means multiplication. And those are the units for momentum. So unlike force, for example, force, mass times acceleration, kilograms times meters per second squared, or in honor of one of the greatest minds in human history, Sir Isaac Newton, we just call this a Newton. Right? Momentum does not have a unit specifically. It just has this combined units. Oops. And on to an easy problem, a problem which you'd never see on a diploma exam because it's way too easy. But we're going to do it anyway. The 1,000-kilogram car is moving at 10 kilometers per hour. Determine the momentum of the car. Just a reminder that One way to do physics problems or math problems too is write down what you have, write down what you want, find a formula. We have the math, and it's in kilograms, which is great. We have the velocity. It is not in meters per second, unfortunately. It's 10 kilometers per hour, which of course we must convert to meters per second. And that equals 2.8 meters per second. Let's just remind ourselves to get from kilometers per hour to meters per second, we just divide by 3.6. To get from meters per second to kilometers per hour, we multiply by 3.6, and then we can proceed with our question. We're looking for determine the momentum of the car, P equals mv, or sorry, I should have done P equals question mark, and then P equals mv, and plug in the numbers, 1,000 times 2.8, and we get the answer of 2.8 times 10 to the 3 kilograms meters per second. Okay, correct amount of significant digits, 2 here, so 2 in our answer. So the concept of momentum is a pretty simple one. It gets way more complicated when we move on to impulse. Impulse, even though the formula is not any more complicated, it's just the concept of impulse will make you think a wee bit more than momentum. The simple definition for impulse, that is a change in momentum. Since impulse means momentum is change, the object must be moving at a different velocity. So if you have a change in momentum, remember this is delta. Delta means change in, equals, it could be a change in mass, could be a change in mass, could be a change in velocity, or it could be one or the other. What is more likely in the physical world that we exist in? Definitely a change in velocity. Right? The only way that you could do a change in mass is, let's say you're calculating the momentum of a football player and he's running 75 kilograms, and let's make it easy. He's 100 kilograms and he's running at 10 meters per second, which is unbelievably fast, right? So he would have a momentum of 1,000. The only way that the mass could change is if he was running and he chopped off his arm or something, and then all of a sudden when he weighs 99 kilograms because his arm was a full kilogram. So more likely it's going to be a change in velocity. So here's our formula for impulse. Delta P equals m delta V. And a reminder that the change in velocity is always going to equal the final minus the initial. The change in anything always equals the final minus the initial. Delta E, energy, change in energy. Final energy minus the initial energy. Example number 2 says a box of Tic Tacs sliding along a table 5 meters per second. I try to stop it, but only slow it to 1.6 because it's so heavy. Determine the impulse I impart to the box. Mass, 0.015 kilograms, right? 15 grams, change it to kilograms. 5 is the initial velocity, 5.0 meters per second. I try to stop it, but only slow it, so the final velocity is 1.6 meters per second. Determine the impulse I impart, delta P, question mark. Here's our formula, delta P equals m delta V, and we're going to just expand that to be VF minus VI. And you probably already know you're going to get a negative number here, aren't you? Because this is going to be 0.015. The final velocity is 1.6. The initial velocity is 5. That's going to yield a negative number. And it turns out to be negative 0.051 kilograms meters per second. And of course, the units for impulse are the same as the units for momentum. The negative simply indicates that it was in a negative direction, right? In other words, what was the direction? If I'm pushing the Tic Tacs, the box of Tic Tacs to the right, which direction was the impulse? It was to the left. Okay, so that's what the negative indicates, which makes sense. I mean, the change, it's slowing down, so really it's accelerating in that direction. If you remember the whole lesson on negative acceleration from Physics 20. Okay, and moving on. So now here's where it starts to get a little more interesting. And that is when we talk about Newton and Newton's second law of motion, which we commonly associate with this formula here. It appears as this on your formula sheet. Just a reminder, F net over ma, but usually we like to see that. It's nice and easy to remember. And here's where we talk about the quantity of motion. And this is how Isaac Newton started. He started with this formula here. He said that force was a change in momentum divided by a change in time. Right? So not F equals ma. That's what he started off with. But since we just did impulse and we know that the change in momentum is mass times the change in velocity, then we can substitute that in to get this formula here, right? Instead of this, we're going to write m delta v, and we have a new formula, F equals m delta v over t, but it says we also know from physics 20 that acceleration equals a change in velocity divided by a change in time. And that's how we end up with this formula that is so familiar to us, F equals ma, right? We can take this right here, and we can just substitute a in for that. So this is just how these formulas came to be. And now we have, this formula that we started with. We have this new formula, and of course we can solve this new formula for delta p and get this. So now all of a sudden we have two different formulas for impulse. Wow. And just to verify that those formulas are actually legit, let's just do a quick unit analysis here. If I'm looking at this formula here, I'm going to say that the units are kilograms mass times meters per second. Well, what about this one here? What about this guy? I'm going to say that that's, force is measured in newtons and time is measured in seconds. Ooh, those don't look the same. Well, of course they are, because if I change newtons, I know that a newton, F equals ma, a newton is a kilogram meter per second squared. So if I change this to kilograms meters per second squared multiplied by seconds, I can clearly see that this cancels out this, and I'm left with kilograms meters per second, just like this one. So yes, they are equivalent. And if impulse equals this and impulse equals that, then this must equal that. And this is the formula you're going to see on your formula sheet. It's right here. It's a classic formula. It's great because you can use one side or the other side or both sides, right, as it says right here. And you can solve for any different variable here. So I can rearrange it for force. I could get force equals, oopsie, equals that. Or I could arrange it for mass. I could get mass equals that. All kinds of permutations and things you can do here. Ooh, here we go. Example number 3. Example number 3, and then we'll split this into 2 lessons because I've done a lot of unnecessary talking. Rifle is firing a 9-kilogram bullet. M 0.009 kilograms. Change it to kilograms. So that leaves the muzzle after 2 2.4 times 10 to the negative 2 seconds, traveling at a velocity of, now, what is this? 247 meters per second. Is that V? Is that VF? Is that VI? Or is that delta V? Well, we would assume that the bullet starts from rest, so we can just call it delta V. A rifle is firing a bullet, so that leaves the muzzle traveling at that velocity. So that is the delta V. Really, it's V, it's really VF, the final velocity, but VI is 0, and therefore VF is the same thing. Right, 247 minus 0 is 247. Determine the average force. So we're looking for force, question mark. There's our 4 variables, and we just highlighted this wonderful formula. We're solving for force, so that's pretty easy. Plug in the numbers. And 247 divided by 2.4 times 10 to the negative 2, and you are going to get an answer of 93 newtons, which may not seem like a lot. However, we're talking about 9 grams is not a lot of mass. Okay, so we're going to stop there because it's a 16-minute video, and that's quite long, and then we'll do the rest in part 2. See you then.